Hello everyone. My name is Daniele. It's my first time at this conference and I'm very excited to be here. Today I'm going to talk about my team's journey in developing a system based on secure multi-party computation for cross-organizational analytics. I am a privacy engineer in Resolve, which is a company based in Denmark doing ad tech. So we're going to talk about our journey, as I said. First, I'm going to introduce you to the scenario we're working with, our vision to develop a system for democratizing private analytics with SMPC, Secure Multi-Party Computation, some open source tools that we used, and the modification we had to do to them. And the hope is that this is going to be of inspiration for some people that are working with similar problems, or at least can spark some discussion within the community. So let's start with cross-organizational analytics. Let's say we want to compute a function, any kind of analytics. Let's take histograms as an example between three parties, and we want to protect their input data. We work in the ad tech space, so it could be that there is an advertiser that is running a campaign across three different publishers. So news site that sells ad space. And they want to check periodically, daily for instance, whether some users have reached the so-called frequency cap. So they don't want to overexpose the users. This is just a use case, but it could just be that we want to compute an histogram with the different contribution. We cannot do that because of two reasons. First, privacy, but there is also a second reason. Normally, this organization wants also to protect their competitive advantage, and they don't want to share their data also for this reason. How do we solve it? Well, one way is to use secure multi-party computation, and that's what I'm going to talk about today. There are many ways to do secure multi-party computation. I'm going to talk specifically about additive secret shares, which means that we divide in different numbers that add up the contribution of single parties. Like if we have a 10, we are going to split it in 5, 2, and 3. We want to see this secure multi-party computation system as a black box. So we would like to not to worry all the time on developing new protocols for different use cases. We want to focus on the business logic. We would like to have some SMPC system where the privacy and security guarantees are underneath, are given. However, the libraries or the tools that exist usually are not so user-friendly and not so fast. Before going on, I need to do a disclaimer, because we are going to use secure multi-party computation to protect input data. We do not protect output data in this case. We can do that with differential privacy, for instance, but that's not the focus of this talk. And I'm going to use analytics as an example, but you can do more complex computation, such as training machine learning models as well. So what was our vision? Our vision was to create a system for democratizing private analytics with secure multi-party computation. What do I mean by democratizing? I mean that I would like to enable developers that are not multi-party computation experts to perform private analytics. I would like developers to focus on the business logic, to develop the functionalities. I really don't want them to worry about the privacy guarantees all the time, because every time they should change a protocol, they should read papers, and so on and so forth. So we looked for tools, different tools available, and we found one tool, one framework, which is called MP-SPDZ, is a friendly MPC framework, is available online on GitHub, is under active development, and is very well maintained. There are different protocols with different security models: malicious security, covert security, which is in between, and semi-honest security. The good thing about all these protocols is that they are split in an offline and online phase. The offline phase is where we say that we generate some materials, which is called in jargon correlated randomness, which is data independent. This means that we can generate all this offline material before, and then when the time of the computation comes, we can be faster. And the good thing, as I said, is that it's data independent. Moreover, it has this Python-like interface. There are some limitations to that, which is not having dictionaries or hash maps. And the memory is allocated at compile time, so the data structure cannot grow at runtime. And we're going to see later how we overcome these challenges. But now we have these frameworks. And as I said before, our objective is to give it to developers, or to develop a system that developers can use to build analytics. But how do we deploy it in the real world? Well, we looked again, and we found Carbyne Stack, which is an open source project, again, to enable cloud-native secure multi-party computation. Just for information, Carbyne Stack was developed by Bosch Research in Germany, and it has been recently donated to the Linux Foundation Europe in order to further support the growth of this open source project. And Resolve has a place in the technical steering committee in this project. But why did we choose Carbyne Stack? Well, I said it's open source. It has an active community from both industry and academia. It's a way to deploy and scale our favorite framework, MP-SPDZ, but actually you can also use another one if you want. And then, finally, it has this client-server style multi-party computation, which means that there are two kinds of actors, data providers and computational parties. And the data providers just provide the data and offload the computation to the computational parties. So you can do a lightweight deployment on these data providers, which maybe don't want to be a computational party. And the good thing is that no party at any time sees the raw data. The data are split in secret shares, and these secret shares are uploaded to the secret store of computational parties. Carbyne Stack, as I said, is cloud native, so it means that it enables, we can scale the system very easily, and it's also fault tolerant. It serves as an execution service for our library, MP-SPDZ, but also as a generator and storage of this offline material that, as I said before, is data independent, and it's a huge advantage. But we could do some extension to this system to make it more usable in the real world. First of all, the security model that Carbyne Stack supported, it's a covert security model, which could be quite strict, and it's also expensive to run for many reasons. So we asked ourselves whether we could modify the system to use a semi-honest model. Secondly, we know that all these secure multi-party computation protocols are network bandwidth heavy. They have many rounds of computation. So can we optimize the infrastructure? Finally, can we also improve the parallelism of our algorithms? Well, we focused on these three areas for our system enhancements, and I'm going to now present to you all of them. First, the security model. We implemented support for a semi-honest security model, which is more efficient in the real world. And of course, it has less security guarantees per se, but this is compensated by the fact that the parties are bound by legal contracts, at least in our scenarios, but it's something to consider. Then we actually added the support for this offline material that I was telling you about before, because in this covert security model, the tuples are also also have a MAC, a message authentication for authenticating the message. Instead, in semi-honest, there is no MAC, so you can they are much smaller to generate as well. At infrastructure level, instead, we asked, where do we put the computational parties? Well, first of all, disclaimer from a threat modeling viewpoint as well, the data are already in the cloud in our case. So we do not upload data to the cloud. They are already there, in AWS specifically. So we could put the computational parties in the same data center, the same availability zone, which is basically a data center. And we could do VPC peering. In AWS, if you do VPC peering within the same availability zone, suddenly the networking cost drops to $0 per gigabyte. Moreover, we gain also on the latency because it goes to 1 millisecond compared to 25 milliseconds if it was between two different zones. There is one more thing that I think was very nice. We run on spot nodes. What are spot nodes? Spot nodes are basically spare capacity that the cloud provider has, and it's significantly cheaper to run your application on spot nodes. There is a downside. These are non-reserved capacity, so that it can be taken away at any time. So you have to deal with more frequent crash scenarios. We had to implement an orchestrator for the execution service to deal with the retry of failed workers. But it's also acceptable to take slightly longer to our application, in particular if your application runs in parallel. And I'm going to talk about this in a minute. But let's zoom out a little bit. Let's talk about what we wanted to give developers. We wanted to give to developers a general functionality. So we decided to focus on the group by for analytics. It could be a primitive that we give to the developers, and also the joins between two datasets can be implemented with group by and union, for instance. So it was good. But we don't have dictionaries, right? So we cannot really do fancy things. So we implemented the group by with a sorting plus accumulation approach. Sorting requires a lot of binary operation and comparison. So we had to add the support in Carbyne Stack for cryptographic primitives called the bits and the bits for more efficient binary operations. It was already in MP-SPDZ, but not in Carbyne Stack. On a higher level, how does our algorithm work? So every party, offline, they split the data using a bucketing technique with an hash function, which then the different data goes to different buckets. There is a local sorting, and then this SMPC comes in place, because every partition is sorted in parallel in a secure way with this SMPC that we can see, again, as a black box. And then all the results are combined. All the data structure are fixed, though. As I said before, MP-SPDZ doesn't allow to grow data structure at runtime. For this reason, we had to use a padding technique to match the different data structure size. So finally, to wrap up, with this project, we demonstrate that practical MPC, practical secure multi-party computation is possible, and it could be a tool to assure privacy and also be made available to developers that are non-multi-party computation experts. There are promising open source projects, such as the one I talked about today, Carbyne Stack and MP-SPDZ, to make them usable in the real world. And in your scenario, you may have to do some system enhancement. You can consider to use a semi-honest model, for instance, or you can modify your algorithms to run in parallel, as we did, for example. to parallelize at least a part of it. Finally, there are some infrastructure optimization that you can do, such as zone affinity, so running the computational parties in the same zone or in the same data center, or running part of it in spot nodes. So that was it. I hope that this could be of inspiration for people working on non-MPC or looking into it. Thank you very much for your time. Thank you very much to my team, which are these guys that did the most of the heavy lifting in this one.